Okay, this is hour 2 for Physics 1b. We're going to talk about the speed of a wave on a string. Okay, so your book goes through kind of a derivation of this. It's not something that I don't personally find it particularly meaningful. I think it's better to just kind of understand what this equation represents. So I'm going to write down the equation, and we'll talk about what it means. So the speed of a wave on a string is a function of two things. It's a function of t, which in this case is the tension within the string. And it's a function of mu, where mu is the linear mass density. It's basically the mass of the string divided by the length of the string. So it's the mass divided by the length. This is referred to as linear mass density. Now, this equation is kind of more generally true if you characterize these quantities in a slightly different way. So the quantity that shows up in the denominator is the inertial quantity associated with the medium, and the quantity in the numerator is effectively kind of how the medium interacts with itself, how pieces of the medium interact themselves. So if we were talking about the velocity of sound in air, this would take on a slightly different form, but it would still have the same kind of general properties. That the thing that shows up in the bottom would be the density of the air, and the thing that shows up in the top would be what's called the bulk modulus. But it's generally the same idea, that basically the velocity of a wave on a string or in any other substance is inversely proportional to kind of the density of the substance, right? That always shows up in the bottom. So the speed is going to be higher if you have a string that's really skinny, and it's going to be a lot lower if you have a string or a cable that's really thick. You can think about like the difference between a wave that might travel along a guitar string versus, which is very light, versus the velocity of a wave that might travel on, say, an extension cable, which is very heavy. All right, so that's the speed of a wave on a string. And that's really all I'm going to say about it, other than to kind of do a problem where we can see how this is applied. Right here. These problems are quite long, so it's really tiny writing. Hopefully you guys can all read this. All right. So you got a picture right here of what's going on. One end of a 2 kilogram rope is tied to a support at the top of a mine. A shaft that's 80 meters deep. The rope is stretched taut by a 20 kilogram box of rocks attached to the bottom. So there's some rocks attached down here. They're 20 kilograms. The mass of the rope is 2 kilograms. A geologist at the bottom of the shaft signals to a colleague at the top by jerking the rope sideways. So this person down here jerks the rope. What's the speed of a transverse wave on the rope? If a point on the rope is in transverse simple harmonic motion with a frequency of 2 hertz, how many cycles of the wave are there in the rope's length? Okay, so as we said above, the velocity in this case is equal to the square root of the tension in the string divided by the mass density, mu. Again, mu is equal to basically the mass of the string divided by the length of the string. Right? I guess I should give you all a little bit of time to try this problem. Do you all want to give this one a shot? See what you can figure out here. So try to solve part A, and if you can get that one, try to solve part B, and I'll give you like 5 minutes. So it's 11:21 right now, so we'll check back in 11:26. If you do have any questions, feel free to ask. You can ask in the chat. You can open your mic and ask whatever you want to do.
Okay, for A, did anyone get like the square root of 800g?
I think that's right. 88.5. And I guess y'all are assuming that the rope is massless, probably. Is that right? No, I'm sorry. I meant for the tension. I know the rope has mass, but for the tension part of it, yeah. Okay. That is fine. Yeah, 88.5 is the right answer for the first part. So if you haven't already gotten that, see if you can get it. And once you've already gotten that one, try part B.
Does it 2 times per second? So it's times per second, so it should be 2 times the velocity, which is. So wouldn't it be 2 times the square root of 800g for part B?
Not a no.
No. Okay, wait. Frequency is.
Just use
okay,
the velocity equals wavelength times frequency. Just remember that, and you can figure it out from there.
Yeah. Okay.
And John has the right answer as well. 1.8 is right. And the period is 1/2. That's right. Okay, that's 5 minutes, a little over 5 minutes. So let's go ahead and, as you all figured this out already, let's go ahead and do this. So the tension on our rope here is basically going to be, as you all figured out, it's basically the mass of the samples multiplied by g. And then we divide by mu, which is this. This is the mass of the string, or it's called the rope, I guess, divided by the length. So if we plug those in, we got 20 kilograms multiplied by, let's use just 9.8 meters per second squared for this. And we divide by mass of the rope, which was 2 kilograms. Again, we're assuming that the tension is entirely produced by this 20 kilogram mass at the bottom, and we're ignoring the mass of the rope. We probably, I mean, it's 2 kilograms. I don't think it's totally reasonable to ignore the mass of the rope, because it will contribute a little bit to the tension as well, but that's okay. Mass of the rope is 2 kilograms, and then we're dividing this by the length, which is 80 meters. Take the square root of all of that. The square root goes over all this stuff. So yeah, the 2's cancel, so you said 800g, and then if you actually calculate this out, you end up getting, as John was saying, 88.5. So that's our velocity. And if you think, this is kind of interesting, right? The velocity is entirely determined by, it's not like how hard you whip the rope or how fast you're moving it back and forth. It's just determined by the medium, right? And how kind of connected the medium is, how much tension there is in that medium. So it's important to remember that any problem you're doing, that you don't need to know anything about the wavelength, the frequency to figure this out. This is independent of the wavelength and the frequency, except that it's equal to the wavelength times the frequency. It has another way of finding it, right? All right, that's part A. Part B, if the point is in transverse simple harmonic motion with a frequency of 2 hertz, I want to find how many cycles of the wave are there in the rope's length. We can do this by saying that one cycle has a wavelength lambda, and lambda is equal to the velocity divided by the frequency. So we take 88.5, and we divide by the frequency of 2 hertz. So we're going to get a wavelength that's half of this, which would be like 44.25 or 44.3 or so. Let's write it as 44.25 meters. And then to find how many cycles, which is one wavelength, are there in the length of the rope, then we would just take the length of the rope and divide by the wavelength. So we'd end up getting, it's almost 2, but not quite. It's like about 1.8 cycles. Okay, pretty easy. Pretty easy. We'll use this idea of the velocity of the wave on a string further when we start discussing what are called standing waves, and we want to relate. We can kind of see it already here, right? There's a connection between frequency, wavelength, and velocity. And what we'll find later on is that's going to affect kind of the pitch that's produced by a stringed instrument. One thing you can see that's a hint of that right here, if we look at that equation. If you think, any of you that have played a guitar or a piano or any type of a stringed instrument, violin, fiddle, cello, any of those things, let's just think about the guitar. At the top of the head of a guitar, you've got the strings are all attached to these knobs, and when you twist those knobs, what happens on your guitar? For those of you that have played guitar before. Those little knobs, they're at the head of the... Here, should I draw it?
It kind of like decreases or increases tension.
Yeah, it changes the tension, right? So if you've got a guitar, right, it's constructed of... You've got this long arm, you've got strings that come down this way, right? You've got your little opening here that's the cavity that's used to kind of echo the sound, right? But right up here at the top, each one of these strings is tied to a knob, and by twisting the knob, you change the tension. And then, as Delvino says, by changing the tension, you change the pitch. And the pitch is... What's pitch another word for? Delvino, do you know? Is it the wavelength? Is it the frequency? Which one is it? When we say the word pitch. It's okay if you don't know it. It's actually frequency. But they're all tied together, right? They're all tied together. Anyway. Yeah, 50-50. Yeah, 50-50 shot. So the point is that by manipulating the tension in the string, you change the velocity. And what we're going to learn is that the wavelength is actually something that's related to the length of the string. So with that being, that distance is fixed on a guitar, right? That's your wavelength. Technically, it's half the wavelength. And by just increasing the tension here, you can modify the pitch. So you can, quote, tune the guitar, right? You can tune it so that the string so that it's producing the right pitch, so that when you hold down the appropriate notes here, you get exactly the key that you're expecting, whether it's a G or if it's a chord or whatever you're getting out of that. So, anyway. And there's something else you can see inside of here too, right? The velocity is inversely proportional to the mass density, right? So on a guitar, these strings, they don't all have the same mass density, right? They go from really skinny strings, which produce really high pitches, so that's low mass density, to really thick strings that are often made of like wound up little coils. And those have high mass density, which means a slow velocity, and then that velocity can affect the frequency too. Right? Anyway, so this is all, we'll get to that at the end. of today, but I just wanted to kind of note that contained within that equation of the velocity equal to square root of t over mu, it basically is at the core of how a guitar is designed, right? You've got your thick strings down here, you've got your tiny, thinny, skinny strings up here, and, you know, this allows you to produce all kinds of different notes. All kinds of different notes that then become music when played in the right order. Okay, so the next thing we want to do is to introduce the wave equation. So this is a powerful idea that it arises out of this discussion of waves, and it shows up all over the place in physics. So let's think about our wave function that we found, right? So we found a wave function. That was represented by y of x comma t, and that was given by the one that we used was a times the cosine of kx minus omega t, right? So let's talk about some things that we can do with this. So first of all, one thing we could do is say, we know that if we know the position as a function of time of a particle on a string, for example, since we have a function of time, we can describe the velocity, right? The y component of the velocity, which would be the rate at which the string is oscillating up and down. To attach that back to here, that would be the rate at which this is moving back and up and down. It's not constant, but if I know y is a function of time like this, how could I find the velocity of a point on the string? If you think back to physics 1a. If I've got position as a function of time, and I want to get velocity as a function of time, what could I do? We use calculus, right? Well, which type of derivative do we want to take? Do we want to take a derivative with respect to x or a derivative with respect to t, or some kind of combination?
Would it be a derivative with respect to time?
T. Yeah, time, right? This would give us the velocity, the y component of the velocity, right? You take the derivative of y with respect to t. Okay, so if we do that in the equation right here, what we're going to get is negative a omega. The negative omega I pulled out right here, but when you take the derivative of a cosine, you'll get another negative sign. So you'll get a omega times the sine of kx minus omega t. Now what I've done here, if you haven't taken multivariable calculus, which I guess is, what is that, 220 for you guys? You may not have seen this before, but I can explain what we've done pretty simply. First of all, does that look right? Is that the right derivative? Yeah, we call this a partial derivative. That's right. Now, to find a partial derivative, what you do is you treat any variable that's not t as a constant. So in this equation here that we started with, there's two variables, right? The two variables are x and t. And there's a whole lot of constants. A is a constant, k is a constant, omega is a constant. Now, as a student, you look at this equation, you might think, oh, there's 5 variables, but in reality here, y is a function of only x and t, which means x and t are the things that vary in the function, but a, k, and omega don't, right? So if you ask the question, how do I take the derivative of y with respect to t, what do I do with the x? And the answer is you just treat the x as if it's a constant. That's pretty much it. You treat it as if it's a constant. That's partial derivative. Okay, we could also find, let's use the same color. We could also find the y component of the acceleration here. And to do that, we would take the second partial of y with respect to t, which means we take the derivative of this equation, And now we take the derivative of sine, and we just get cosine. But we have to take the derivative of the inside as well. So we're going to end up getting a, there's going to be another omega, so we get omega squared. And then we have a negative sign now. So we're going to stop right there. That gives us the y component of velocity and the y component of the acceleration. And then side by side this, we're going to do some other thing. So we just did the partial derivative of y with respect to t. What if we then check out the partial derivative of y with respect to x? What does this represent? If I take the rate at which y changes with respect to x, what does that represent?
Basically, like how fast it's going, and its direction based on its position.
Yeah, but when you use the word fast, you've already said something about time, right?
Yeah, okay.
So I'll make this a little simpler. So first of all, when I take a partial of y with respect to x, what that means is I'm treating the t as a constant, right? So suppose that I gave you this function. I say y of x is equal to 2 meters multiplied by the cosine of, what's a good value for k? It doesn't really matter, does it? Let's just say that it's just 3x. And then this thing is a constant, right? So I'm just gonna put in here that this is minus a constant, okay? And we don't care what it is. So we don't care what it is, I can pick whatever I want, right? So let's make it 3x minus 10. Okay? So I give you this function. At its core, it used to be a function of x and t, but we've kind of plugged in our own value for t and omega here, right? If I now take del y del x, what is that going to give me a representation of? And again, if the partial derivative is messing you up, now that I've gotten rid of the t, there's nothing wrong with just calling it a full derivative, actually. What does that represent? What does dy dx represent? This is simpler than you think it is, by the way. In case if you're making it really complicated, I promise you it's not complicated. What does dy dx represent? Just go way back to your Cop 1 days. Okay, you say velocity with respect to the x-axis. It's not exactly right, because velocity implies time, right? When you say velocity, what's another way of saying that word? What's another word you could replace that with without using the... It's the change of x. Displacement, not exactly. What is dy dx? We can make this even simpler. I can get rid of the cosine function if it helps, but... Slope. This is slope. That's right. It's the rate of change of y with respect to x, right? That's it, just slope, right? And so if I take the partial derivative of y with respect to x, what that's going to give me is a representation of the slope of my curve. Right? At any point in time, let's go back to our picture here. If we freeze time, like we have here, we just like let time go, but then we freeze it, right? Every point on our curve has a certain slope, right? This point right here has a slope of 0. This has a slope of 0. This is where our maximum slope occurs, right? And then in between, you have different values of slope, right? And if we take the derivative of our function, you get the slope at every point in space, right? The rate of change of y with respect to x. So that's what the slope is. So let's write this down. What would it be? If I take the derivative of this one, I'm going to get a k that comes out in front, right? And I'm taking a derivative of cosine, so I'll get a negative sign. So I think we're going to get negative k times a. And then sine of kx minus omega t. All right. What happens if I take, and again, when you take the partial derivative, you just ignore the time. The time basically is just a constant. It's just a constant. What happens if I take, this part, I definitely won't be surprised if you don't know what this one is, because I don't think it's commonly taught at El Camino. Probably, or really at most undergraduate institutions. What do you get when you take the second derivative of y with respect to x? Does anyone know? So concavity, right? That's a jerk now. Arc length. There's an equation you can write down where it's like 1 minus this. You take the square root, you can find arc length. That's arc length. That's right, John. I probably got that wrong, but it's something like that. So concavity, the sign of this will give you a concavity, right? If it's positive, it's concave up. If it's negative, it's concave down. But what this thing actually tells you is called curvature. I don't know if I can fit this in here. Curvature. It tells you how curvy it is, which I guess concavity is a general way of saying that to some extent. So it's the curvature of the line. So what's this one going to be? We take the derivative of this again, and we're going to get negative k squared multiplied by a, and then multiplied by the cosine again of kx minus omega t. I very often make mistakes in calculus when I'm talking and writing, so if you see any mistakes, please let me know. Right? Cosine derivative of that is negative sine. Derivative of negative sine is negative cosine. And each time we do this derivative with respect to x, we're going to plot a k, right? All right, so we've got these two equations, and you might notice they're really similar to each other. In fact, what we can do is we can kind of equate them to each other. So, what would be the best way to write this? So I would say that if we put these two equations together, this is what we're going to get. The second derivative with respect to time, sorry. The second derivative of our wave function with respect to time, it looks like it's almost exactly equal to this one. They both have this same feature, right? They have a cosine, they have a negative sign. So they look exactly the same, except there's one thing that's different, and that is that one of these has omega squared in front of it, and one of them has k squared in front of it. So what we could do is we could say that, oh, whoops. Meant to put an x right there. That these two look the same, except that one of them, this one has an omega squared on it, and this one has a k squared on it. So in order to make them exactly equal to each other, I think what we could do is something like this. Does that look right? Does that look like it would work out? You can kind of work it out for yourself if you just plug del 2y del t2 is this whole thing, plug it in here, the omega squareds cancel, and you get a k squared. It looks right, right? Okay. We can write this in even a more general way because omega and k are related to each other, right? So just to remind you, omega was equal to 2 pi times frequency, right? And k was equal to 2 pi divided by lambda, so k over omega would be what? It'd be 2 pi over lambda divided by... Here, wait, let's do it the other way, because this looks confusing to me. Let's do omega over k. That's usually the way we write it. Omega divided by k, which is the inverse of the thing in front, is 2 pi f divided by 2 pi and then divide by lambda. So this is equal to lambda times f, which means that omega over k is the same thing as velocity, right? So k over omega squared then, we could write like this. 1 divided by the velocity of the wave squared multiplied by the second derivative of y with respect to t is equal to the second derivative of y with respect to x. And this is what we call the wave equation. Any function y that satisfies this differential equation, it's a partial differential equation, any function y that satisfies this will be a wave. So the wave equation says that basically any function that satisfies that equation Any function that satisfies that differential equation will represent a traveling wave. Okay, so this is where we can generalize things beyond just this one type of wave function. This is only one type of wave function here. Okay, this is a sinusoidal wave function, but there are an infinite number of different types of wave functions, and I don't mean just by changing k and omega. I mean, we can change the cosine part of this too, because really any function that has this kind of feature inside of it, this kx minus omega t, and I'm going to write it in a more general way, but as long as you have that little piece right there, it will automatically satisfy this equation. Guaranteed. It doesn't matter what the function is. So in general, I can represent any of these functions by saying that any function that looks like this f. Let's write. Yeah, I want to write like this. Any function of the form f of x minus vt, or f of kx minus omega t will automatically satisfy that equation. And you can prove this for yourself if you want to. Will automatically satisfy the wave equation. Any function. And if you don't believe me, I'll try to prove it for you. So, as an example, what if I give you a function like this? So y of x and t is equal to 1 divided by, let's do something really simple, x minus 3t squared plus 1. Now you look at that equation, and you tell me, does that look like a wave? You can plot it on your calculator if you want to. I mean, it's not easy to plot because you've got x and t, right? So it's difficult. You kind of have to pick values of t here. But you could ask the question, is this a wave? Or could this represent a wave? What does your intuition tell you? My intuition when I was a student told me that only sine waves and cosine waves were waves. That's what I thought. I don't know what y'all think, but to me, if I was a student, I would say that doesn't look like a wave. But according to what we're saying here, anything that satisfies this wave equation will be a wave, and this is a function that definitely takes on this form, right? It's a function of x minus vt, and v is 3, right? So let's plot it. Let's see what it looks like. I think you'll agree that it looks like a wave, and then we'll do the math to prove that it satisfies this here. Let's use Wolfram alpha. Okay, we're gonna plot the function that I wrote down there. Here, let me just kind of go like this, like this. So that's what we want to plot, right? So we're gonna plot 1 divided by x minus 3t. So I can't just put t in here. I don't think that's going to work very well. So what I'm going to put in here is I'm going to put t equal to 1. We're going to square that, and then we're going to add 1. I'm only adding 1 here, actually. I'll show you what happens if we don't add 1 first. Here. Let me show you what happens when we don't put a 1 in there. You're going to need a pole or singularity, and it'll go off the screen. But if we add a 1 in the denominator, we'll get a pulse. See, we got this little pulse right here. That looks even better. That kind of looks like a pulse of a wave, right? All right, so now what if we want to understand what it means for the time to change? How do we make this wave travel? Well, it's easy. All we have to do is to take our function and then just increment the time. So we'll plot this same function 3 times. Oh, I didn't copy the... Gotta close the parentheses here. And the only thing I'm going to change here is I'm going to change the time to 2 seconds. I'm going to change the time to 3 seconds. And then we should get 3 pulses, one representing t equal to 1 seconds, one representing a second later at t equal to 2 seconds, and then one representing t equal to 3 seconds. We plot those three functions, we'll get a traveling wave. Here's our wave at t equal to 1, here's our wave at t equal to 2, here's our wave at t equal to 3. It's a pulse that travels to the right, right? It's just like, if we go back to our, this thing right here, it's just like this one, right? Little pulse that travels along the wave. That's a wave. So even though intuitively this function does not look like a traveling wave, I mean, for me personally, it is. This represents a wave that travels like a single pulse. It doesn't repeat like a sine wave does, but nonetheless, it's still a traveling wave. And the reason why is because it has this form, and any function of this form will automatically satisfy the wave equation. Okay, does that make sense? Does anyone have questions? So, from a physics and mathematics perspective, this is truly what a wave is, right? So we said at the beginning that a wave requires a medium and a disturbance, right? And the disturbance needs to be able to propagate through the medium. That's what you need for a wave. The wave equation, what it does is it generalizes that idea. This equation represents the general form of what a wave is. It generalizes it away from like a particular example, right? A wave in water is an example. A wave on a string is an example. But what they have in common is they both move in such a way that their curvature is related to their acceleration divided by the velocity squared. That's the key thing. The curvature of the wave is equal to the acceleration of the wave divided by the velocity squared. All right. Anyone have any questions? Okay, do we want to show why this satisfies this? I thought that's probably useful to do, right? So you can do this yourself, or I can do it. I don't know which one's more valuable. But this requires us to take the derivative with respect to time twice of this. So let's do that. Let's prove that this satisfies the wave equation. All right, this is going to be a little trickier. Let's see. So del y del t is going to be equal to... this one's awful. Because we're going to have to do... whatever. We'll just do it. It's going to require we use like the quotient rule and stuff, which you'll have to remind me. So if someone wants to go look up the quotient rule, or if you remember what it is, I think I know what it is. We'll see. The derivative of this with respect to time. So we have to take the derivative of the first part of it, which I believe is going to be something like this. So we have to decrease the power by 1. So the denominator was to the -1 power, now it's to the -2 power. And we need to multiply by the derivative of the inside. So that's this piece right here. So we have the derivative of this would be 2 times... Oh, we're doing time first, right? So x minus 3t. And then we have to multiply by 3 on the front. So this will become a 6. This is a derivative calculator, but it's wonky sometimes. Well, I mean, Wolfram Alpha will do derivatives. Wolfram Alpha will definitely do derivatives. Yeah, low d high minus high d low divided by low squared. That sounds correct to me. Okay, but let's make sure we got the first part right. Do you all agree with this? Take time to work it out on your own paper. I easily could have made a mistake. You got the same? Great. All right, now the harder part, which is the second derivative. I mean, let's be honest. This isn't It's not that hard, it's just kind of tedious. Okay, low d high. So that's the lower part times the derivative of the upper part, right? And we're only worrying about time. So this would be it's a good thing we don't need to do a third derivative. So low times the derivative of the top. The derivative of the top is just going to be the derivative of a constant is 0. The derivative of this would be -3. Hold up a second here. Shouldn't this have been negative? Yeah? No? What do you guys think? We take the derivative. We should have gotten a negative sign somewhere here. Did it cancel out with something? I did think I just left it off. Because this was from the derivative of the bottom, right? So it was like 2 times x minus 3t times the derivative of the inside of that, which would have given us a negative sign. You're saying the -3t cancels out with the minus? Are you talking about for the second term here? I meant like this. Okay, first of all, before I had a plus sign here, now I'm saying there should be a minus sign. Is this correct or is this incorrect? Just for the first derivative. I'm not talking about the second derivative. Oh, okay. So John, you're saying you thought that there was a minus sign there. Oh, maybe I. Oh my god, excuse me. I don't know if you guys heard that. So, that looks right now, right? Oh, no. I know where it came from. It came from here. It is positive.
Yeah, it is positive.
Because there was a minus sign we brought down from here. Okay, so that's right. Okay, boy, doing calculus on the screen. There was a time when I felt like I was good at calculus, but when I sit in front of people and do it, I always feel like I'm awful at it. All right, so low d high, so this is low. Derivative of the top now is going to give us -18t. That looks correct, right? All right, now we have to do minus high d low divided by low squared. I just start to feel like this becomes really like not the best exercise. We could have made it so much simpler by making that +0 right there, but that's all right. Okay, now we have to take high d low. So we'll have 6 x minus 3t times derivative of the denominator is going to be 2 times x minus 3t squared plus 1. This times the derivative of the inside. Oh, yeah, there's no t here, is it? That's right. There's no t right here. You're right. It's just -18. 6 times -3. All right. Derivative of the bottom, 2 times this, and then we have to multiply the derivative of the inside, which is going to be 2 times this. Times -3. And we need to square the denominator, right? That feels right. -3 times 2 times 2. All right. So altogether, we end up with this function right here. And the one thing I notice is that the -3 and the -6 are going to make it. Oops. It's going to become plus 18 when you combine those together. I'm going to leave these other 2's where they are for a reason that we'll see here in a second. Does that look okay? This is something where I feel like if I just wrote this down on a piece of paper, it'd be really easy for me to do, but when I'm looking at the screen and talking, it's really easy to make mistakes. Let's just check. So it's low d high. So we replaced the bottom part shows up there. And then we took the derivative of the top, which was 6 times -3, which is -18. And then we rewrote the top again, which was 6 times x minus 3t. That was this part right here was 6 times x minus 3t. We took the derivative of the bottom, which means that we have to bring the 2 down in front. We rewrite the function. We take the derivative of the inside, which is the derivative of this part. So we'll get another 2 times this, but then we have to again take the derivative of the inside of this, which gives us another -3, and that -3 times the -6 out here became a positive 18. Yeah, it looks right to me. Does this look right to y'all? Okay, so now what we would have to do is we'd have to do the exact same thing by taking the derivative with respect to x. And I'd still like to talk about a lot of other things today, so I don't know that it's super valuable to do this, but I'm just going to emphasize one thing that's going to happen here. When we do the exact same process with x, okay, we're basically going to get the exact same function here. And I'm going to leave this as for you all to work out because, again, it's going to take a while to do it. But we're literally going to get the exact same function, but the difference is going to be here. The difference is going to be this 18 that shows up here. 18 is 9 times 2. 9 is the velocity squared. So I guarantee you that if you take the derivative with respect to x, what you're going to get is the exact same thing, except where there's an 18, there's going to be a 2 in both cases. And that will effectively prove that when you take the y derivative with respect to t twice, you multiply by 1 over v squared, you'll get this. And if you want to try this yourself, pick an easier function. Like make this 0, and it'll be a lot easier to prove. In fact, I think I did that with my 1C class. We're going to go on break, but I can just show you. We're covering the same topic on 1C. What happens in 1C, in case you want to know. So here, this is the wave equation again, right? Same thing. Difference is that the speed is the velocity of light, and instead of having the y-coordinate, it ends up being what's called the electric field. Let me see if I can find where we did the wave equation example here, because we can go through and it's a lot simpler to follow. Here we go. It's so much less work. It's like 3 lines. So this one's a little easier. So it's the exact same function, except I didn't put the +1, and as a result, you can kind of like look through that and see what happens if you want to. So anyway, get the exact same functions. The difference is the velocity squared shows up right here. All right, so this kind of taught me that it's always better to use simple examples, I think. All right, it's 12:08 though. We need to take another break before we come back. So let's stop for now.